Welcome to GiulioBursiOptics, your channel for non-imaging tutorials. Today we'll talk about Etendue, or how to not have a miserable life when designing narrow beams. When I worked in the industry, narrow beams were a constant hot topic. Someone would come to me and say, "Giulio, can you design me a lamp that puts out a ton of light in a 5-degree beam using a 50mm optics?" The answer is no, that's simply not possible. Let's see why. Let's start with a standard TIR lens. Focusing central zone, flat output surface, very basic. We'll simulate 3 different light sources: a near point source, a 6mm source and a 9mm one, and see what happens to the beam angle in each case. Let's start with the point source. The light comes out almost perfectly collimated. Nearly all the rays, aside from a few stray ones, sit within a very tight cone. Looking at the angular distribution, the candela plot, the half width is roughly 2.5 degrees. So we're looking at a total beam angle of about 5 to 6 degrees. Now let's simulate the 6mm one. We see now that some rays pick up a noticeable angle and the beam is no longer collimated. The candela plot half width jumps to about 7 degrees, giving a total beam of roughly 15 degrees. Lastly, with a 9mm LED, we see that many more rays deviate significantly from zero and the plot spreads out further still. A half width around 10 degrees, so we have a total beam of around 20. Same lens, 3 different beams. Did we just design a bad lens? Maybe, but you could spend months optimizing it and still hand your manager nothing usable, because there is a hard physical reason you can go below a certain beam angle with a given lens. That isn't a design problem, it's physics. Let's switch to a new schematic and focus on the left-hand side. We have the light source, the horizontal line, emitting light upwards. I've drawn just the axial ray, the ray that originates at the center of the source and travels straight along the optical axis at 0 degrees. Of course, a real error source doesn't emit just one ray. It emits infinitely many, spread across both its physical extent and its full angular range. Depending on the source, that angular range might be narrow, or in the case of a Lambertian source, it can cover the full 90 degrees of the hemisphere. Each ray originates from a random point on the source and lives at a random angle within that emission cone. How do we represent this? Position of origin and angle in a single 2D diagram. Simple. Put special position on the horizontal axis and angle on the vertical axis. Let's start by plotting the axial ray. This starts at the center of the distribution and travels at 0 degrees, so it will be placed in the middle on the x-axis and at a 0 level on the y-axis, on the vertical axis. Let's add more rays now. We see that this new ray starts off-center. The angle is roughly 45 degrees, so on the plot is on the side with respect to the axial ray, and on the vertical range it is quite in the middle. Let's add more rays and we see that the plot fills in. Since rays can originate anywhere across the source and at any angle within that emission range, the points trace out a rectangle. Formally, this rectangle represents an area or volume in phase space. And at Etendue, the quantity we are discussing today is that phase space volume. Etendue is calculated as the product of the square of the refraction index, pi, the emission surface, and the square sinus of the half emission angle. We are calculating Etendue just outside the LED surface. So we are in air, so the refraction index will be 1. And we have a Lambertian source, so the half angle is 90 degrees. So the contribute of the sine will be 1. The measurement unit is quite unusual, millimeter square times steradian. But for our example, let's focus on the numerical value. We got around 1000 millimeter square steradian. So, what happens when this light passes through a lens, a refractor? Let's take the same 50 mm lens from our earlier simulation and squeeze the source's light into it. The output distribution comes out looking quite different. To calculate the Etendue of the output side, we take the beam area, approximated here as the lens diameter, 50 mm, as a simplification, since a real lens has edges and other details we are ignoring for the moment. Suppose our target is a 5 degrees beam. In that case, the Etendue of that output distribution would be only around 100 mm square steradian. But wait, we're trying to squeeze a source with 1000 of Etendue into an optical system that can only carry 100. Something clearly doesn't add up. That something is a conservation law, because Etendue can never decrease in an optical system. It's a direct consequence of the second law of thermodynamics, arguably the very one law of physics you really don't want to mess with. Etendue can only stay the same or increase in an optical system. And that happens, for example, where light gets scattered by a frosted or satin finish. Etendue can never go down. The only apparent exception is if you're willing to accept a system efficiency well below 100%, say 10%. Technically, that would work, in the sense that the numbers would kinda balance out. But designing a lamp with a 10% efficiency just so you can pair an oversized LED with an undersized lens makes no practical sense. So, to actually get a clean 5 degrees beam out of that 50 mm lens, how big can the LED be? Let's shrink the source until its Etendue is comparable to what the lens can handle. Around 5-4 mm, we start landing on comparable values. Assuming a realistic lens efficiency of around 85-90%, the source output can now realistically fit in the distribution. So, a 50 mm lens producing a 5 degrees beam can handle a source no larger than about 5 mm in diameter, nowhere close to the 14 mm LED that we started with. Or the other way around, if we need to keep that 14 mm LED, say because the project calls for 3000 lumens, how big would the lens need to be to capture all that light? Even at 100 mm diameter, we're still not there. Only by relaxing the beam angle to around 8 degrees does a 100 mm lens becomes large enough to capture essentially all of a Etendue produced by that 14 mm source. So what's our takeaway from this long discussion? There is a hard physical limit, not a design limitation, a physical one, linking source size and beam angle for any given lens diameter. It is simply not possible to produce a very narrow beam from a relatively large LED using a relatively small lens, no matter how much time you throw at the optimization. So before you spend weeks or months trying to design your way around this limit, just don't. It's not a lens problem, it's the second law of thermodynamics. Thanks for watching and see you in the next video.